When you look at an ordinary differential equation, you are looking at an infinite number of possible mathematical paths. Our goal is to isolate the single perfect path and lock it into an exact target. To get there, we take a proposed function, calculate its derivatives, verify it algebraically, and solve for a particular solution. Before we start, make sure you are comfortable executing the power rule and the product rule. You will need them to calculate higher-order derivatives accurately. You also need to watch out for the constant of integration, the arbitrary letter c. Dropping that constant during your calculations will ruin the final equation. Solving differential equations is a systematic process. We take a generic formula of change, apply strict mathematical rules, and narrow it down to a singular, verified curve. Step 1 is identifying the order of the ordinary differential equation. An ODE is simply an equation that involves the derivatives of a function. To find its order, you scan the equation to find the highest derivative present. You might see Leibniz notation, Lagrange notation with prime marks, or Newton dot notation. These all mean the exact same thing. Watch out for this notation trap. Parentheses around the 4 indicates a fourth derivative. Without parentheses, it is just the function raised to the fourth power. Properly reading this notation tells you exactly how deep you need to go in your calculations. The highest order identified serves as a strict map. If the equation is third order, you must differentiate your starting function 3 consecutive times. Step 2 is calculating those required derivatives. We take the proposed function and differentiate it consecutively until we reach the target order we just identified. Look at this equation, x squared cosine x. To differentiate this, use the product rule. Keep the first and second part distinct as you apply the formula. For the second derivative, carefully track your negative signs. Missing a distributed negative sign, or forgetting the derivative of cosine is negative sign, will break the equation as errors cascade. Use caution when applying the power rule to fractional exponents. If you differentiate x to the 1/2, remember that subtracting 1 leaves you with a negative 1/2 exponent. And remember the basic rules. The derivative of a constant will always drop to 0 during these consecutive steps. Maintaining absolute precision in all these intermediate calculation steps determines whether the final ODE verification succeeds or fails. Step 3 is verification. We take our freshly calculated derivatives and plug them straight back into the starting ODE through algebraic substitution. On the left side is our original ODE, y prime minus 5y equals 0. On the right, we substitute our proposed solution, e to the 5x, and its derivative, 5e to the 5x, into those variable positions. Next, we walk through the algebraic simplification. Multiplying the expressions gives us 5e to the 5x minus 5e to the 5x. Because those terms cancel perfectly, the equation resolves cleanly to 0 equals 0. Achieving a perfectly balanced mathematical statement like this is the definitive proof required to verify that the general solution is valid. A verified general solution still includes the arbitrary constant c. To finish the problem, we must find the particular solution by solving for that constant. This coordinate graph shows the general solution y equals x squared plus c. Because c can be any value, this formula represents an infinite family of parabolas stacked here on the graph. To lock down the exact equation, we apply an initial condition. This real-world constraint requires the curve to pass precisely through the coordinate 1, 4. By plugging these coordinate values into our general equation, 1 for x and 4 for y, we algebraically solve to find c equals 3. We construct our fully resolved equation by replacing c with 3, giving us y equals x squared plus 3. Applying the initial condition is the vital step that transforms an infinite family of solutions into the singular actionable formula needed to map the system. We have completed the workflow. We decoded the raw ODE, calculated the necessary derivatives, verified the proof by balancing the equation, and solved for the exact constant. Look at the graph again. With the constant solved, all the incorrect paths fall away, leaving only the single curve intersecting flawlessly through our target coordinate. As you work through these problems, check your parentheses notation to confirm the order, track your negative during product rules, and make sure your verification step balances completely. Stick to this checklist on your homework and exams, and you will be able to verify any solution accurately. Mastering ordinary differential equations gives you a rigorous, step-by-step method to definitively prove how a system behaves from a specific starting point.